In our last video for chapter 18, we're going to kind of wrap everything together by first using the Arenediazonium salt to look at adding other substituents onto the benzene ring, look at nucleophilic aromatic substitution, and then finish by looking at intramolecular reactions and forming cyclic compounds. Okay, so as I mentioned at the beginning, the Arenediazonium salt first. What's that guy look like? Well, it's up top here. Okay. And that's something that's really useful, right? An Arenediazonium salt, benzene diazonium chloride down there in the bottom left. Really useful because it readily reacts due to the stability of nitrogen gas that's emitted as the reaction comes in, right? Nucleophile comes in and replaces it. See that upward arrow next to N2? That means that a gas is being evolved in the reaction, right? Nitrogen gas in this case. So that allows nucleophiles to substitute in for the diazonium group. Okay. How is the diazonium group made, the salt, anyway? Well, it's not stable, so you can't pull it off the shelf, right? It has to be made in situ. Notice 0 degrees Celsius there, with a solution of HCl, right, and sodium nitrite, NaNO2. And that'll take you to your diazonium salt, and then that thing reacts immediately, depending on what else you put in solution. Okay, here's a way to put on a halogen. These are called Sandmeyer reactions, okay? Named reaction, a Sandmeyer reaction. That's something that uses a copper salt specifically. Notice we've got copper bromide, copper chloride, and copper cyanide here. Any one of those will come in, right? And the negatively charged group, bromide, chloride, or cyanide, will come in and replace N2 there. Okay, so you've put on a new nucleophile, and this happens by a radical mechanism. You don't need to know how it works. Know that the Sandmeyer reaction is useful for controlling the positions of these things, right? Because if I were to do a dibromination or a dichlorination, right, my first group that's on there would become an ortho and para director, right? So I would get a mixture of the products, right? But if I'm working with a diazonium salt and I use a Sandmeyer reaction, then I only get one, the ortho, or in this case, as the slide shows, the para product, whichever one you choose to start with when you control your diazonium salt. You can also add iodine by using potassium iodide with a diazonium salt. Okay, no copper here, that's not a Sandmeyer reaction. And the Scheiman reaction is the only way to add fluorine to a benzene ring, right? Starting with the Arenediazonium salt and then adding HBF4 and heat, right? Only way we've seen to add fluorine to the ring. Okay. Or if you leave your Arenediazonium salt to just warm up, it makes a phenol. Okay, so it's 0 degrees Celsius to make it. That warms up, slightly acidic solution, you're going to form phenol. Okay. You can get a higher yield by adding copper oxide and copper nitrate. Right? That'll help your yield overall. Lastly, you can replace a diazonium salt with hydrogen, right, which is useful if you have to use the amino group that's on there, for example, as a director, but then you don't want it in your final product, which you would need to do to make 1,3,5-tribromobenzene here. Use the NH2, and then when you don't want it on there anymore, you can replace it, okay? And that's done by using hypophosphorus acid, H3PO2 there. Notice the name, H3PO2, hypophosphorus acid. It's not phosphoric acid, which people commonly mistake it for, which would be H3PO4. So we can use this in our retrosynthesis. Okay? For example, here, if I'm trying to make, I alluded to this before, right, meta-dibromobenzene, that first bromine would be an ortho-para director, so I could never get it to be in the meta position. That would require first the bromination and then a Sandmeyer reaction. Okay, so the synthesis is shown there on the bottom. So now let's think about that Arenediazonium acting as an electrophile, okay, because it's got a positive charge there. It can do that. Okay, keep in mind that Arenediazonium is only stable at 0 degrees Celsius. Okay, so it has to be at a cooler temperature, meaning it's only going to react with our most active benzene derivatives, right? Notice OH here, strongly activated. Okay, but as long as you have that, then you can form a new compound there with that NN linkage called an azo linkage. So here we're forming azobenzene. Okay, but the mechanism is the same as all of our EASRs in the past, And notice here we're only showing the para compound, even though OH phenol there is an orthopara director, just because of sterics. That's a big electrophile that's coming in, so para is going to be favored over ortho. But as you see here, the mechanism is the exact same. With that NN double bond, our azobenzene could be cis or trans, but just be looking out for the fact that trans is more stable, again, because of sterics. With those big rings, we don't want them hanging out next together like they are in this Mickey Mouse looking compound. So how is that diazonium produced? Okay. The electrophile that's used in solution is the nitrosium ion, NO+, right there, nitrosium. That's what's required to make the Arenediazonium salt. And nitrosium is formed when water is eliminated from protonated nitrous acid, HNO2. Mechanism for that is shown here. And then once we have it, here's the mechanism for forming the diazonium salt. Okay. I'm not as concerned at this stage with your knowing how to make the diazonium salt, but know why it's useful for things like Sandmeyer and Scheiman. Okay. So that finishes that part of the video. As promised, we're jumping in next to nucleophilic aromatic substitution, which is the flip side of what we talked about. And really, I said at the beginning, right, wasn't possible. We said that, okay, we've got benzene, it's got the pi cloud of electrons above and below the ring. So it's not going to react with any nucleophile because they have like partial charges. But okay, it is possible if there are substituents that are electron withdrawing. Okay. You can do a nucleophilic aromatic substitution if you have a strongly electron withdrawing group, either ortho or para to whatever group you're substituting. So notice we have our NO2 group here. That's strongly electron withdrawing, and it's in the para position up top, then para and ortho, and then para and both ortho. Okay. Because the more electron withdrawing groups you have in those ortho or para positions, the better yield you get and the easier reaction you do. Notice the conditions are getting milder as we go from top to bottom. At the temperature, we're able to cool it down and work with less harsh conditions in terms of the basicity. Well, now why does that electron withdrawing group have to be in the ortho or para position? It's because of a two-step mechanism here, and specifically what's going on in the middle. Okay. In our mechanism, we have the nucleophile that comes in and attacks the group that's being replaced. Okay. The carbon that's across ortho or para anyway to the electron withdrawing group. Okay. And then that forms a resonance stabilized carbanion intermediate. It's known as a Meisenheimer complex. And you see how that carbanion is stabilized throughout the ring, similar to how our positive charge was before. Okay. And then when we reestablish the aromaticity over here, our leaving group is eliminated. So the mechanism's a nucleophilic substitution, but overall it's pretty similar to what we've seen in the past. And keep in mind that the incoming nucleophile, Y in this case, has to be a stronger base than the substituent X that it's replacing. Because just like we've always said since the beginning of the semester, you can only ever eliminate a weaker base, right? Weaker base, better leaving group. Right? And then this talks about why it has to be in the ortho or para position, because as you saw on the previous slide, that's the only way for our electrons to be delocalized and be more stable. Doesn't happen if you're in the meta position. Okay. So here we have some examples of a nucleophilic aromatic substitution reaction. It's just another way to replace substituents if you have a strongly electron withdrawing group, ortho or para. Two examples here. We finished the video with intramolecular reactions. And just like we've always said, everything we looked at previously was intermolecular. Now we're looking at intramolecular. Okay, things happening within. It's only going to happen if we form a 5 or a 6-membered ring. I could make a ketone, right, from a Friedel-Crafts acylation, benzene in this case, with our acyl chloride. Right, that would work if you have an acyl chloride or an acid anhydride over here. Right. You just got to control the number of carbons in the middle because you're only going to get a 5 or a 6-membered ring. Different way to do it, maybe we wanted to make a lactone. And if you remember that term from chapter 15 when it was introduced, right? A lactone, a cyclic ester. All right, we could do that from a carboxylic acid and an alcohol. It's no different. Now we're just thinking about it, jumping back again a slide here, with an electrophilic aromatic substitution reaction. No different from the things that we've seen before. Here is an intramolecular Williamson ether synthesis, which we saw back in chapter 10. No rules that are different. And well, there are rules. There are no different rules than what we've seen before, right? 5- and 6-membered rings are what we're looking for. We can do it as well with a benzene ring. And those products themselves can undergo further reactions, right? I could make a ring, and then here I could brominate, right, with NBS going into that position there, like we know from chapter 12 is favorable. Kind of wrapping those ideas from all these different chapters together in one. So that wraps up the last video for chapter 18. From this video, know the Arenediazonium salt, know nucleophilic aromatic substitution, and just have on your radar, right, the fact that these intramolecular reactions can form as well to give you a cyclic product.